Good afternoon, or I guess it's not afternoon yet, so good morning still. I'm Priscilla West, and I'm a student at the Banneker Aztlán Institute, and I did research this summer with Professor Charlie Conroy and with Dr. Philip Cargyle. And so I just wanted to start off by asking, how many people here have actually seen the Milky Way with their unaided eye? Yeah, how remarkable is the magnitude of just that small strip of the disk that we can see in our night sky? It's pretty amazing. And so today I'm going to talk about how we can understand more about the formation and evolution of the Milky Way by studying its stellar halo. And understanding more about this is really important because understanding more about our own galaxy's formation history, which is really difficult given that we're inside of it and it's very hard to analyze a system with which we are within, will tell us more about galaxy evolution as a whole and help us understand more about how our universe has gotten to the point at which it's at today. And so with that, let's talk about the stellar halo. So the Milky Way is made up of many different components, right? There's the thin disk, which has the youngest stars. There's a lot of gas in this area as well. And then the thick disk has slightly older stars. We'll call them middle-aged. The bulge around the center, not that there's anything wrong with that. The bulge, you're welcome, around the center of the galaxy has even older stars than any found in the disk. But the halo is where the oldest stars in the galaxy are found. And this is really important because this makes this a great area, a key area for understanding more about the formation and evolution of the galaxy as a whole, because it's essentially a fundamental building block of the galaxy. And so what makes up the actual stellar halo are globular clusters, disrupted dwarf galaxies, open clusters. And I want to show you this simulation done by Johnston and Bullock, and it is showing the actual formation of the Milky Way stellar halo. And so what you're seeing, all of these different colored blobs are clusters, globular clusters, dwarf galaxies, and they're interacting with the Milky Way there at the center of our galaxy, or the Milky Way in general, our galaxy. And as you can see, once they start kind of joining our galaxy, the shape of them changes, and they turn into these very stream-like shapes. And you can think of the stellar halo as kind of a lake. A lake can be made up of many different streams that are leading into it, and you can look at a sample of water from the lake. You can look at its chemical composition, maybe its velocity profile, and you can determine where did this water come from, what stream did it come from. You can do the exact same thing with the stellar halo. We look at these stars, and we can look at their velocity, not just their radial velocity, and their chemical composition, and we can determine what streams, and therefore what clusters they were originally a part of. And so what that looks like in our actual night sky is this. This is a picture from the SDSS collaboration. This is the Milky Way. And this is what the sky looks like in the northern hemisphere and in the southern hemisphere. And I really wanted to highlight specific streams. They're color-coded based off of whether they're all from the stars are from the same cluster or not. And you can see, especially in this blue one over here, this very apparent stream-like shape. And so using the velocity and chemical composition, we can learn more about these stars. So how we're doing that, the data that we're using for that, partially is from Gaia. Gaia is a survey that is going on right now. This is an artist's interpretation of what the instrument looks like. It's actually out in our solar system right now. And it's using parallax to determine the distance, right ascension, declination, and proper motion for about 1 billion stars. And that's really remarkable. It's great to have all these parameters. However, it is only determining the radial velocity for the brightest stars, and specifically, as of right now, stars with a G magnitude of 12 or brighter. And the halo, like I said earlier, is made up of very old stars, and they're very far away, so they're very faint. So our stars, actually, that we're interested in looking at can have a brightness as low as a G magnitude of like 18. And so that's because of the instrument that we're using. And so this prevents a significant portion of the stars we're interested in looking at from having their radial velocity measured as a part of this data. And why that's really important, why we even need the radial velocity, is because this helps us understand more about the actual velocity of the stars as a whole. So proper motion gives us, for example, like the Vx and Vy gives us 2 components of velocity, but that third component that we really need to analyze the dynamics of the stars comes from radial velocity. So without it, we can't learn anything about the velocity. And so that is why spectra is needed for the complete picture. So H3 is a survey being done by Professor Conroy's research group, and it stands for hectoshell in the halo at high resolution. This is hectoshell, the instrument, for which about 100,000 spectra are being obtained. And this spectra is going to obtain that missing radial velocity component, as well as the composition of these stars. And so this is going to really complement the Gaia data set and help us get a full picture of what these stars that make up the stellar halo are really like, the parameters for them. So what I did this summer, the very first thing I did, was matching catalogs, was matching specifically Gaia and H3. And so I used the right ascension and declination, the coordinates of the stars, to match them. I wrote a code that found the minimum distance between the stars in each catalog and matched them that way. And as I said earlier, Gaia has a lot of stars. So it's expected that stars that are within Gaia are not going to be in H3 because we have significantly less stars in our survey. And so because of that, it's really important for us to distinguish which stars we actually have all of the parameters for, which is why we needed to do this in the first place. And so once we had this list of which stars we knew we had spectra and photometry for, I chose 5 stars in M67. M67 is an open cluster. It is very, very well studied. So things like the age, distance, metallicity, radial velocity are very well-known values, and that makes this a great tester for seeing how well our fit does compared to these values. And so this is a color magnitude diagram I made of M67 using the photometry from Gaia. On the y-axis, we have the G-band magnitude, and on the x-axis, we have B minus R. Gaia specifically uses a naming convention BP minus RP. That's why that's different. And these red dots are the 5 stars I chose. And I really want to highlight that they're very spread out over this color magnitude diagram and why that is. So if you were doing a survey on academia, you wouldn't just talk to undergrad students, right? Or you wouldn't just talk to grad students or just professors. You would want a really representative sample of everyone from who's a part of that. And so in the same exact way, we want a really representative sample of the stars that make up this cluster. And so we chose stars in different evolutionary states of their lives, which is what you're seeing here. So once I had those 5 stars, I fit them using something called the pane. And so it's named after Dr. Cecilia Payne-Gaposchkin. The story behind that is really great, and if you're interested, please feel free to ask. I'm going to go right into explaining what the pane actually does. So the pane, it takes the observational data and it is giving us actual physical quantities from this data. And the way that it does that is it takes the spectrophotometry we give it, and it has this interpolated grid. And what the interpolated grid is it's essentially this grid, for lack of a better word, that for specific parameter values, so for example, for a very specific, like one value of temperature, surface gravity, radial velocity, it'll create a spectrum of a star. And then it compares that, it fits it to the actual spectrum we're feeding in from our spectra, and it takes that fit and it throws it into a sample, and it does this over and over and over for a bunch of different spectrums from the interpolated grid. And that sampler, what it does is it gives us the best fit parameter for our actual data that we're getting. So what we get out of it are these derived parameters. And what's so remarkable about that is that we're taking this observational data and we're getting actual physics out of it, like physical quantities, such as effective temperature, surface gravity, radial velocity, metallicity, alpha abundance, reddening, specifically in the visible, rotational velocity, the radius of the star, and the distance to the star. And this is a lot of parameters, so I'm not going to go through all of them. I'm really just going to focus on a few, specifically the effective temperature, surface gravity, metallicity, and radial velocity. And so this plot has a lot going on, so let's talk about it. So these at the end are histograms. They should look somewhat familiar maybe to people. So this is showing you the fit for each of the actual individual values. So this is the temperature, surface gravity, metallicity, and radial velocity. And as you can see, for the most part, they're very well constrained. They have a nice Gaussian distribution for them. There is something funky going on with this metallicity, right? It has a bimodal distribution present. And it's obvious that some error has occurred. And and that this is the least constrained value, and we're going to get more into that in the next slide. But I really want to talk about something really fascinating about corner plots is that these plots within here, these are actually showing the relationship, correlations between multiple parameters. So this is a plot of the radial velocity and the effective temperature, and metallicity and effective temperature. So this allows you to look at any correlations that might be present in your actual parameters that you're looking at. And so I also would like to show you the fit for a spectrum. So this is the Payne's fit for a star, and in the black, that's the actual spectrum of the star that was observed, and the purple over it is the fit that the Payne did. And this is actually quite a small range of wavelengths. It's 200 angstroms. And why this wavelength range was chosen was because there are a lot of very strong lines present, which gives us a really good value for radial velocity. And there's also, if you can see these 3 lines, this is a magnesium-1 triplet, and it is especially sensitive to surface gravity. So it fluctuates based on that, and so this also helps us constrain the value for surface gravity very well. So let's talk about that metallicity, right? This is a plot of the different metallicity values from the stars that I ran through the Payne compared to the literature value. And as you can see, even though that was the least constrained value, these actual values aren't that far off from the literature value. And let's talk about why that might have happened. So for one, we changed the type of sampling that we were doing. We noticed that there was some biasing going on from the preliminary runs that we had with the stars in M67. And so we changed the sampling like halfway through. And this code takes a long time to run. It's ranged from 5 hours to 32 hours for just one star. And so because of that, I haven't been able to run as many samples as we would have liked to really get parameters that we thought fit, and kind of tweaking around with the code and the sampling and priors and stuff like that. And so it's, as you can see, certain parameters do need refinement, and that's something that we do know. However, continually running more and more stuff through this is only going to increase its accuracy, because regardless of what the output may be, the fact that we're getting this output at all helps us go back and analyze what we need to work on, what needs a little bit of tweaking and refinement. So the fits for the stars from the Payne are only going to increase in accuracy the more and more we do this. And so the Payne is going to be extremely useful, an extremely useful tool in the analysis of the Milky Way and its stellar halo through its ability to take this observational data and, like I said, produce physical quantities from it. And so the next time that you see the Milky Way, or the first time that you see it, which I really, really want you to take the opportunity to do if you do have the chance, I want you to just take a second to appreciate the individual components of the galaxy that make up this really large system that we're a very active part of. And with that, I want to list my acknowledgments. These are specifically, I could list everyone like Jamie did. I didn't. This is specifically people who've really helped me with the research project, but I also want to thank, of course, everyone who's helped me as a person, and the Banneker Aztlán Institute, just in general, all of the leadership, our peer mentors, the amazing grad students who, on their own free time, have worked with us nonstop and taken the time to teach us. Yes, they're awesome. As well as, most importantly to me, sorry everyone else, my cohort, because without you guys, this would not have been the same. So thank you guys for that. Thank you for your time and for your attention. Do you have any questions?
Yes. Questions back here. Is there another hand up? And then up here?
Okay, so I just want to, I guess more clarifying question. So you're using 100,000. So you have spectra on 100,000 stars, roughly speaking, and you're running each of those through the Payne, and that is fitting. Like, I guess I'm hearing it's like, so you showed the spectrum of the magnesium triplet, and like I'm just really impressed by the fit. So like pretty much every single like iron line, magnesium line, whatever else is there, and I'm like, that's crazy.
Yeah. So that spectrum specifically is not the one that was from that corner plot. That's actually, I have I have it right here. That's this one. This is from a paper written by Yuan Senting, Dr. Yuan Senting, who wrote the pane, along with Dr. Philip Cargyle. And yeah, as you can see, their runs look a lot nicer than mine. These parameters are very constrained. You can see very obvious correlations between things like the effective temperature and surface gravity. Yeah, and that fit to the spectrum is really, really remarkable. And this is the photometry as well for that. I didn't include that. Yes. Yeah, it's really cool.
So are you gonna like try to take that? Because I remember you're running this on like your laptop. And so, like, is there like plans to like put that on like a cluster or something that just would that speed it up? You know, like. Yeah.
Oh, I'm sure it would. Like multiple processors would definitely speed it up. But my computer, this isn't her, but she's done well for for how old she is.
Wondering about your error bars, because I wonder if like there were some error bars associated with your data that like you may see an overlap with the literature there.
Yeah. So the error bars, so I'd like to emphasize first of all how small the actual error bars for the literature are. They're 0.1, I believe. And the error bars, the reason we don't have error bars for the pane is because of the actual output from it. It doesn't actually, the runs that I did not give error bars for it. And that has to do with the actual way that it fits it. That is something that I was actually talking to Professor Conroy about. And so, yeah, that would definitely, I think, improve how we are able to view the overlap between them. But as of right now, I don't remember the exact explanation. I'm sorry, but it has to do with the fit and the way that the spectrum is fit. I don't remember exactly. I'm really sorry.
There's a tendency for these spectral fits to greatly underestimate the error bars, so you often don't get a good sense of what the true error should be, particularly since it doesn't capture systematic errors. One more in the back here.
This is actually, I didn't realize when I was looking at this during your talk. Wonderful talk, by the way.
Thank you.
But is this the metallicity measured from red clump main sequence turn off red giant?
Yes.
So why would you expect those all to necessarily be the same?
Why would we expect them all to be the same? Because the stars in M67 they're all the same age. So their differences lie in their masses, but they should all have, it does differ. I actually was going through a paper yesterday that was analyzing different stars. And so we do expect, differences in the metallicity, but they should have some mean cluster value because these stars are all formed around the same time, regardless of where they all may be, because of their individual masses and whatnot. But this is compared to like a mean cluster value, really. So, yeah.
All right, well, let's thank Priscilla one more time.